I'll read these, Amelia too, if you want to read these chats. I don't want to, I will read them all. I just don't want to stop and read while we're doing this. So that's a tsunami. A tsunami is the Japanese word for port or harbor, and then wave or sea. As you'll see in the next couple of slides, these waves are only dangerous and large when they approach the shore. And the shape of the coastline and the continental shelf will dictate how much of a wave run-up you get. You'll do a little bit with wave run-ups in the lab. So they're seismic waves. They are like earthquake waves, right? The surface waves that we talked about. And it is, right, port or harbor, wave or sea. There's actually a bigger term that's called, or word that's called imanami. I may have mentioned it the first day of classes. That means wave of purification, which is what this one in many regards was, at least regionally. It's a wave so large that there was just nothing left. It was just bare soil, or not even soil, bare rock. And so we'll also talk a little bit about the Sumatra tsunami. To me, I mean, you can't put a relative value on human lives, but that was worse for a lot of reasons. The death toll was orders of magnitude higher. It was estimated to be about 230,000, but that's just the bodies that they found. So people think that it was up towards 1 million people who died in the Sumatra tsunami. So those are big earthquakes, big waves. So let's continue on with, and I will read the chat in a second. I know it's awful, it's awful. So tsunami is a wave that has a long wavelength, and wavelength is simply the point between, or the distance between successive crests. So this is one wave, this is another wave. The highest point on both waves, that is the wavelength. So that's measured in units of length, so meters, feet, miles, whatever. And then they have long wave periods. That would make sense because these are the same things, but from the successive crests, you measure, instead of in units of length, you measure them in units of time. So it would be like if you're standing there watching the tsunami wave with a stopwatch, and you have one, and then you start your stopwatch, and then the crest of the next one comes, and you click it again. The speeds of these are immense. They're about a jet airplane speed. So this is in kilometers. If you're more comfortable with imperial unit, it would be about 540 miles per hour. Again, about the speed that a jet engine goes. So to make a distinction between the waves that you're used to seeing in the ocean and tsunami waves, and the waves that you see in the ocean, really, they dramatize these in films, Hollywood films, so that it looks like just larger versions of wind-generated waves. So the top picture here, you see that these are wind-generated waves, and water's not really moving much at all. There's this orbital motion, so the water just kind of goes in a circle, and you have these not concentric, but circles one beneath the other, and in this way, energy moves through the water, but the water stays largely still. So if you were ever swimming in the water, right, and a wave comes at you, you would sort of slide up the front, you would be on the crest and then slide down the back, and you'd be right where you were before. So these are waves where energy is moving through the water, which is staying still, and the energy comes from wind blowing on the waves. In the case of a tsunami, see the bottom picture, it's quite a different configuration. It's a wall of water, and it's a very wide wave. So you see the water flowing straight in that bottom picture there. It's a very, very wide wave. And again, depending on the shape of the coastline and the shape of the continental shelf, you can get them to be pretty large. Here's another picture. This is from Press and Seaver in the 90s. They did a lot of sort of physics of tsunami studying and modeling and calculations. And these are just some random kind of numbers of a tsunami. So it's not like you have to memorize these or that there's some magic number here. What I want you to focus on is the relative numbers and the relative configuration of the speed, the width, and the height. So in the deep ocean, the water that's moving as a result of a displacement that we'll talk about, there are no frictional effects with the seafloor because there's this popping upwards and then it just goes. But when the seafloor starts to rise up and the water gets more and more shallow, you begin to have frictional effects. So you see in the deep water, you have this wave that can be 317,000 feet wide, so enormously wide, and then it's only 20 inches high. So if you're in the deep ocean and there was a boat, it's actually one of the safest places to be in a tsunami is in the deep ocean. You would have just a wave of about 1.5 feet high that is wide, but it's, as you can see, going at a very fast clip. So you would kind of have this bump and that's it, you're done. That was the tsunami. As the tsunami approaches shore, three things happen. One, the frictional effects cause it to slow down, right? So the brakes are put on it. It's interesting. We'll talk about an analogous situation with meteorites when they enter the atmosphere. The brakes are put on, so the tsunami wave gets more and more narrow. You see that this is 5,000 to 10,000 feet now, which is still pretty wide relative to a wind-generated wave, but it's much more narrow than 317,000 feet. And so, obviously you have to do something with the water. The reason tsunami are so bad is because water is essentially incompressible. You can't compress it or expand it the way that we can air. So it peaks, and you see here 100 feet or more. So that's the difference between tsunami in deep ocean and tsunami approaching the shore. Also with these movies, there's this kind of, I don't know, misperception that's perpetuated where you have a wave and it comes and another wave and it comes. In reality, for reasons that we'll discuss, you have concentric circles. And you can think of this as like if you throw a big rock into a pond, you have ripples that emanate out from the point of contact of the rock with the water. So these are the waves that are emanating out, and you can see as the minutes pass, more and more concentric circles are going. This is from Sumatra. So that's a little bit about the physics of the waves, but what causes them? We already said that earthquakes and volcanoes are heavily responsible for tsunami, but you can also get them from a couple of other things. So we'll look at these first. Earthquake. We have earthquakes that happen in the seafloor, right? And the situation is that you have to have a specific type of motion in order to get a tsunami. We talked about transform boundaries like San Andreas Fault in California. You could have a massive earthquake, a 9.5 earthquake in the transform or strike slip sense, and you wouldn't displace the water upwards, so you wouldn't have a tsunami. So it has nothing to do with the size of the earthquake. It has everything to do with the fact that you have a vertical displacement. And you have a vertical displacement. You can see since water is incompressible, that disturbance will perpetuate up to the top of the water column and then manifest itself as these concentric circles of waves that come out. Another thing that has to do, or that will dictate how big the tsunami is actually the material properties of the rock. So remember, we talked about rocks. This is one of the reasons why. If you have a rock that is structurally sound, crystalline, like bedrock, so granite or gneiss or something like that, and you apply the stress and then it breaks, it will break in a relatively smaller sense. There'll be less displacement than if you have weakly consolidated, say, sandstone or shale, some sedimentary rock. So what will happen is you put the stress in, and then when it breaks, there's a much larger displacement because the material fabric of the rock is not as structurally sound or rigid. So there's an inverse relationship between the integrity of the rock, the internal strength of the rock, and the size of the tsunami. The weaker the rock, the bigger the tsunami. The more crystalline and structurally sound the rock, the smaller the tsunami. So here's just another picture to show the normal situation. If you have a strike slip earthquake, doesn't mean that you're going to have a tsunami. It's only when you have a thrust fault or reverse fault or a normal fault, one block of rock thrown upwards relative to another, that you have this propagation upward through the water column and you have these concentric circles. Let's see. Another thing that can generate volcanoes, you read about Krakatoa last week with the 2 weeks ago with the super volcano chapter, exploding volcanic islands. And you might imagine these are even potentially more problematic than earthquakes, because in an earthquake you just have this bang and it's over. in a volcano, you could have days, weeks, or months of an eruption in a coastal area or underwater. We'll look at one at the end of the discussion of tsunami. So there's explosions, right? Especially if you're in a coastal area, you have kind of stratovolcano stuff that is andesite. You have explosions, you have earthquakes going on in there, and you have magma or lava flowing out. And that can cause disturbances in the water column that perpetuate out for as long as the volcano's going off. So long-term tsunami. So earthquakes and volcanoes, the tsunami that happened here, we'll talk about areas under the greatest threat later, but these are the plates, right? And in the slide here, you can see earthquakes on the left and volcanoes on the right. Again, I want to emphasize that it's not, the earthquake itself, it's the type of earthquake. So where's my little green arrow? So over here, most of us are right here in Cambridge, and you have this chain right here of earthquakes and volcanoes, right? This is the mid-ocean ridge, and it's constantly volcanically active, but it's that weaker basaltic stuff, so it just kind of runs out like this. There are also earthquakes, right? Remember all those faults that run perpendicular to the direction of the fault zone, but they're going in a strike-slip fashion, so you're not throwing one block of rock up relative to another. So even though there are plenty of earthquakes and volcanoes in the Atlantic Ocean off the coast of where, again, most of us are, those aren't anything that we consider big threats for earthquakes. Volcanoes, you can see where those are, and you remember where they are. Landslide generated. My little thing back. So either a landslide that occurs in a coastal area, so I put this cartoon diagram up because high relief, so you have a big slope. When you have a landslide, which we'll talk about in a couple of weeks, then what can happen is the material will go down the mountain and dump out into the bay and can fuel a sizable tsunami. So we'll talk about Lituya Bay. I always hate to editorialize here and talk about the case studies because you're going to read about them and you'll see that the videos. I hope you'll take the time to watch the videos. But the Lituya Bay tsunami has the dubious distinction of being the largest tsunami ever in recorded history that humans have ever experienced. It was so large that, let's see, I have the tsunami. Here it is, Howard Ulrich, who was talking about this tsunami that happened as a result of a landslide. There's a longer reference in the book, but the chapter opens by saying it was a wall of water straight up and down, about 200 feet tall, and it was black, totally black from the soil and trees. It was traveling about 70 miles per hour, but it was strangely silent. It was snapping these spruce trees along the side of the bay. They were big spruce trees, probably 400 years old, and it was hitting them so hard it was cutting them off at the stump. There was no way my boat was going to make it over that wave. So this was the largest tsunami that ever... I'm in the middle of a fascinating story. Let's see, Jake. So Amelia, if you don't mind, if you see something pressing, I'll read through the chat. If you see something pressing, a question, then feel free to unmute and ask. And same thing, anyone who's here who has a question, please unmute, show your face or not, and stop me. Because if I sat and monitored the chat, I wouldn't be able to tell you these fascinating stories. So I'll tell you that this tsunami happened. There was an earthquake, and I'll show you a picture of Lituya Bay later. There was an earthquake, and the earthquake caused a landslide that dumped all of this material into the perfect configuration of a relatively narrow bay, and it caused a tsunami. Get this, 1,750 plus or minus feet high. It's an unfathomably high wave. This happened in the 50s, and it was so large that the mathematicians who attempted to model the tsunami told the geologists, you're wrong, it wasn't that high. There's no way a tsunami wave could be that high based on what happened. And the Geologists came back and said, yeah, but the trees are all snapped off that high, and there are marine organisms on the side of the bay, the mountains there, and all of the soil is salt. So I don't know. It seems like it was that. And they went back and forth. The mathematicians are saying, no, it's definitely not. You couldn't have that happen. And then it was only in the, I think, late 80s that people revisited this when computer modeling got a lot better. And the mathematicians finally said, oh, yeah, okay, maybe you're right. But there were all these lines of evidence that showed this huge tsunami. Can you imagine that high, 1,750 feet high? This is another situation where we then talk about the death toll, right? A geoprocess isn't a hazard or disaster unless it kills people. And there were only 2 people that perished. Certainly that's sad, but for the largest tsunami in recorded history, that's pretty good, right? For 2 people. There weren't a lot of people living there. There were fisher people there. So another thing that can happen is a meteorite could come in, and now instead of a displacement at the bottom of the seafloor or as you enter the ocean, you have something from above coming down. We're going to talk about water's material properties the second half of class. Just for now, trust me that water has the highest surface tension of any liquid. So what happens is the meteorite comes in and hits the ocean, and you have this huge depression going down. And so now you have a gradient, and whenever there's a gradient, whenever there's a gradient, then water will try to equalize out that gradient. So you have a low point, a high point. The water will rush in from all sides, overcompensate, and then you go this back and forth like this. Each time you're pushing out another wave in a concentric circle until the waves cease. So the meteorite would be up from the surface. And I said that the Lituya Bay tsunami was the largest tsunami in recorded history. However, we do have evidence of tsunamis from prehistory. And we'll talk about the Chicxulub crater, which is off the coast of the Yucatan Peninsula. It was a meteorite that impacted and was the one that killed the dinosaurs, insofar as you think dinosaurs existed. And the tsunami deposits, you can see by this yellow circle, were so far reaching that they reached New Jersey. So you can imagine the better part of the United States here covered with a tsunami, the likes of what you saw previously, although there were no human structures. So these can be huge depending on the size of the meteorite. So not much to say about this. This is just kind of if you're more of a word person than a visual person, this shows that there's something displaced either at the surface if you're talking about a meteorite, or the bottom of the ocean if you're talking about an earthquake. There's a displacement. Water rushes in from the surrounding areas to try to even out that water, but it gets wildly overcompensated for. And so that's the reason for the first thing that happens in a coastal area is the sea actually retreats, because it's going to meet the lowered area. So water comes from the coastal regions, goes out to meet it, and then you have these waves that travel out in concentric circles. All right, let's see, Amelia, what has gone on? Jake, I said that's a good question about subduction zones. Jake, do you want to, rather than me trying to scroll through this, do you want to unmute your mic and ask your question that way?
Can you hear me?
Ah.
Okay.
Yes.
No, I think you answered it. It was like maybe 10 minutes ago. You were saying that the tsunamis are caused by convergent or subduction edges, never by slipstick, transform, or by divergent edges. Correct?
Right. Right. Correct. So I wouldn't say that it's always a subduction zone. You could actually have localized compression, which would cause a popping upward, similar to how we said glacial rebound in New England is causing earthquakes upwards. You could also, thinking about New England earthquake reasons, remember we said that we're being stretched thin and we're moving at a slower rate than the Pacific side of the North American plate. And so you can have a tensional environment that causes a break and it will, because one block is thrust upward relative to the other one, it will also cause a tsunami. So it can be a subduction zone, and the big Tohoku earthquake that you'll see the documentary of, and you saw the footage of, that was a subduction zone earthquake, but it's not always. It's just that you have some tectonic process where rocks break in a vertical sense. That makes sense? Yeah, okay. So the places where the most tsunami are, the Pacific Ocean, right? This is the Ring of Fire. There are a lot of earthquakes, a lot of volcanoes. The Atlantic coastal areas, we'll talk about those at the end of class like we did last time, or the end of this section. And the Japan, Taiwan island arc, because of those 4 plates that are coming together, you have 2 subduction zones. This is the preponderance of all tsunami. About a quarter of all tsunami that happen in the Japan, Taiwan island arc. And then we'll talk a little bit about Hawaii that gets tsunami from anywhere. I mean, Hawaii is in the middle of the Pacific Ocean, so anything that happens on the edge of the Ring of Fire, it's going to come and smack Hawaii. The good thing about Hawaii, though, is that, and I'm not saying that they didn't suffer from devastating earthquakes, tsunami, like the Hilo, Hawaii, just disaster, but it's a situation where the water is really deep and then gets shallow fairly quickly. So remember, in deep water, tsunami aren't huge in terms of their height. And so the tsunami doesn't have a lot of time to transition from a deep water wave to a shallow water wave. So it kind of comes in really fast and just kind of bounces off. And the same thing happens in California, because California is an active margin. The coast is really really steep going off into the ocean. And so you wouldn't tend to get the shoaling that you would if we had one in Boston, because of our very, very shallowly sloping coastline. Would be bad. Bad. Okay. I'm going to ask you to take a moment to read this. I beg your pardon. My dog is barking. I forgot to put her in. So have a look at this. I'll be right back. Okay, so sorry. So you will see this stuff in the video footage that you'll look at later on. So some of the effects include the first wave versus the second. There's always this discussion of which is more damaging, the first wave versus the second. And the first wave is the largest wave, right? Because that's the largest vertical displacement. As you saw in that beginning video, everything gets pulled along with that wave. And then in between, so going to the next bullet, in between you have this vigorous backwash because the sea recedes before the next one comes. And with the vigorous backwash, you're pulling away. Coastal areas are primarily consisting of sediment, right? Unconsolidated sediment. You're undermining the stability of piers, of anything built in a coastal area. It goes back out. The second wave is almost as big, not quite, but almost as big. But the second wave has all these projectiles in it. Imagine that wave that you saw at the beginning of class, retreating and then coming back. You have all sorts of material in there, natural and also human-made material, boulders, etc. So deposition of boulders is there. The second wave, again, is considered more damaging by some, but there are others who would retort that, yes, but the first wave already destroyed everything. So by the time the second wave comes, there's nothing to destroy. But it is a more dangerous wave, I guess. And in between the retreats, there's an advance, which makes for severe flooding, potentially far inland. Think of the the Chicxulub crater tsunami going over pretty much all of the United States. Those tsunami deposits got there because water brought them there. So you have severe flooding far, far inland. And so kind of mixing these a little bit. With the flooding inland, you have the stripping off of vegetation, of topsoil. And in coastal regions, especially where there are threats of tsunami, right, there probably would be volcanoes that weather into really fertile soil. So if you're practicing agriculture in a coastal region where there's tsunami, you are destroying the soil, you're destroying the crops, and then you're salinating what soil is left there. So you could end up with collapsed agriculture for months or even, a year, depending on how much rain is there to rinse the salt out of the soil. So what else? Coral reef destruction. This is fascinating. So coral reefs, and also those of you have repeat offenders here who took wetland, mangroves are another environment where they are powerful protection against both tsunami and then, as we'll see later, hurricanes. So coral reefs are, these big reefs in shallow water right before the land. And so the tsunami will come in, and as I've written here, will destroy them. But in the process of destroying the coral reef, what happens is the energy is given to the coral reef. So the water that's on the other side of the coral reef going towards the shore is relatively quiet water environment. And I think I said this in Wetland, that when the Sumatra tsunami happened in 2004, as this is my business, I was riveted to the TV, and I was picturing the shape of the coastline and the continental shelf all over the Indian Ocean, and was picturing in my mind which countries would be more devastated by the wave, again, based on, is it just a really steep drop off into the ocean, or is it a shallow situation? And in the days that followed, when the reports of death and destruction were coming back, I was really confused at first, because I thought, well, that's not at all what I would picture in terms of the death tolls of those different countries based on their coast. I keep saying coastline shape. I mean the shape of their continental shelf. Is there one? How big is it? And it turns out later, this made sense to me, and then I started seeing papers about it. Very poor and very rich countries suffered much more lightly. Why? Well, the rich countries kept their coral reefs and maybe did ecotourism or have this environmental preservation and protection in place so that coral reefs weren't destroyed for shrimp fishing and aquaculture. Mangroves, same thing. Very poor countries didn't have the capital to start up aquaculture coastally, so their mangroves and coral reefs are in place still, but because they didn't have the money to destroy them. And sort of middle income, if you will, countries around the Indian Ocean that had enough money to destroy coral reefs, to cut down mangroves for either coastal development, hotels, that sort of thing, or for aquaculture, for shrimp farming, they suffered mightily because there was no barrier between the wave and the land. So it's a little bit about coral reef destruction. Pollution, as we'll see the second half of class, water has properties that enable it to dissolve pretty much anything and keep anything in solution. So anything at the surface of Earth, such as what? Such as, I don't know, a big pile of salt for de-icing, DPW stockyards, such as big piles of coal that people are burning for electricity, such as underground storage tanks, anything that is a pollutant. When the wave grabs it, it will pollute the water. So the tsunami waves aren't very clean. Fire, just like earthquakes, right? You have this wave coming on shore and you saw some fire. I don't know if you noticed it in that little clip that I showed you. You have natural gas lines rupturing. So now you have methane in a volatile scent, and now you have power lines breaking, so live sparks. So often fire and explosion happen associated with tsunami, even though it's water. Loss of life, obviously, massive loss of life, potentially. And then to end this slide on a little bit lighter note, because this is pretty bad, there are diatoms and some alga that can bioluminesce when perturbed. So remember the nuée ardente rolling down the side of a mountain, and if you see that at night, it looks like this glowing ash cloud. If you have a tsunami at night and there are these diatoms and algae present, then what you see is the whole bay suddenly lights up. It looks like it's on fire or it's glowing. So those are called fire sparkles. So another great picture of a tsunami. So you see that it is a wall of water, and then there is a large amount of water coming behind it. So I don't know. I'm supposed to say something else about this? I don't know. So there's the coastline. In terms of monitoring, warning, that sort of thing, we've come really far, really fast, sadly, as a result of the Sumatra and Tohoku earthquakes. There were a lot of gaps that were pointed out that we then rose to the challenge of filling. But the way that we monitor for tsunami is with something called a DART buoy. DART stands for Deep Ocean Space Assessment and Reporting of Tsunami. So Deep Ocean Assessment Reporting Tsunami. If you were to drive by one in a boat, this is what it would look like. If you were to look at a cartoon diagram, cross-section developed by National Oceanic Atmospheric Administration, this is what it would look like. So remember, you have these earthquakes, and you've done the earthquake triangulation lab, right? You have these earthquakes. So it could be that the global teleseism network picks up a relatively large earthquake or monster earthquake, such as the case of the Sumatra and Tohoku earthquakes. Oh gosh, it's a 9.1. That doesn't necessarily mean a tsunami is coming, because if it went in the strike-slip direction, there wouldn't be one. Or if there was a sizable earthquake, but there was not a lot of displacement, the rocks are crystalline, it wouldn't necessarily be an enormous tsunami. So the way that we can tell based on an earthquake that a tsunami is going to happen is by peppering the seafloor with pressure transducers. And so these transducers are at the bottom of the ocean, and they're obviously pressure transducer designed to detect any sort of variation in the pressure on the seafloor, whether it is a huge drop or a huge rise. So what a huge drop would mean is that there's a lowering, right? So that's kind of the space between the wave peaks, because the water column is suddenly, water weighs so much, suddenly lowered. Or a large rise because there's a big wave that is on top of where the pressure transducer is. So the pressure transducer sends, shall I grab the green arrow that I always have problems navigating, sends an acoustic signal through the ocean. Sound travels good through the ocean, up to the surface. There's the DART buoy that you saw on the previous slide. And then this will uplink, I think I can, okay, uplink to a satellite, which will then, through GPS, downlink to a tsunami warning center. We'll talk about these tsunami warning centers. So it's a great system. Instantaneously, pretty much, the tsunami warning system gets an independent verification, or alert rather, that there is a huge drop or huge rise or moderate rise or drop in the pressure at the bottom of the ocean at this location. So therefore, there's a tsunami potentially. Let's issue a warning. So I've been teaching this class for 15 years, and I used to, sad that those two horrible, heartbreaking tsunami happened, but I used to be histrionic about this and say, so this is an older slide, I'm giving you the historical perspective now, that, oh my gosh, if there were ever an earthquake in the Atlantic Ocean, we would have no idea. This is just, you know, absolutely crazy. The Atlantic, but also the Caribbean, right? You have the little Caribbean plate there. We have earthquakes all around that area. Mexico had some sizable earthquakes. And we don't have any DART buoys. I would say, look, this is where we need to have them, or we'll never know. After both of the major earthquakes in 2004 and 2011, we have each one of these symbols is a different Tsunami Warning Center. So PTWC is Pacific Tsunami Warning Center, and we'll talk about the ones in the United States, the Alaska Warning Center. So we have a lot of these, and I just noticed I just updated this slide minutes before we started class, because I wanted to show you the most recent data, and what I failed to see is that, yeah, for some reason they're just talking about the Pacific DART buoys. So you don't see the Atlantic ones, but they are in, so I'll go back one slide. All of these and more are in. So now we are properly outfitted with the potential to predict. And you guys are going to do some work with travel times. So knowing when a tsunami could come. These are a little more predictable because it takes hours potentially from the point of rupture, depending how close to the shore it was, to then to get where we are. In our country, the United States, we have 2 warning centers, one in Palmer, Alaska, West Coast. The Palmer, Alaska one also does the Atlantic Ocean. So when something happens in the Atlantic Ocean, it goes to the Alaska Tsunami Warning Center. And then the Pacific Tsunami Warning Center, which is in Hawaii. So we have these 2. This is another historical perspective because this is scary. This is, I swapped this slide out in 2004, but I just brought it back because I think it's neat to show the progression. It's cool to see that, you know, we're always changing our methods of prediction. So it used to be, this is when I was scaring people, it used to be that if there was an earthquake in the Atlantic Ocean, again, no idea what the configuration is, it would be that the Alaska Tsunami Warning Center would issue a warning, but it just says there was an earthquake. It has nothing to do with pressure, drops or rises. And then the Alaska Tsunami Warning Center would warn the National Weather Service, and the dog is being very difficult today. Cassie, sorry. So the National Weather Service in Melbourne, Florida would get a phone call. It's amazing, right? What if someone was at lunch during the phone call, or a fax, and this is in 2004. And then the National Weather Service, upon receiving the fax, would disseminate the warning through the hurricane hotline that the National Weather Service manned. And then any areas that were deemed to be possibly affected by a tsunami based simply on the magnitude of the earthquake would get a coastal flood warning. So if you've ever gone on weather.com, you'd get a coastal flood warning. So this is a little bit scary, right? So go back one, sorry. But now we have a much better system. We would get instantaneous notification of the pressure drop or rise, which would enable people to say about the size of the tsunami, which you could pretty instantaneously calculate the evacuation zone. So it's not to say that we will lower destruction as a result of tsunami, but we can warn people. So 2004, this is a little animation. Again, I don't want to say too much about this. I could talk about these all day. Heartbreaking, heartbreaking. The human misery that happened here. This is the Sumatra tsunami, and just a couple of facts and figures about it. It was a magnitude 9.2 earthquake. It was about 1,000 mile long rupture, and it displaced about 50 feet. So it was a long rupture, broke upwards, and it was a big earthquake. The largest earthquake that has ever happened is a 9.5 in Chile, and it was a disaster in so many countries. So you'll read about this, and if you want to watch the National Geographic special, great one to watch. It's heartbreaking. The interesting thing is animals. We talked about animals last week. Animals are actually somewhat able to predict a tsunami. And now we know why in the case of a tsunami, because there's a compressional wave that's generated in the air when the tsunami's roaring towards us. And animals that have large ears are best equipped to predict the tsunami. So for example, there was an elephant. I think he was pretty old. He was in this zoo in Sumatra, and he was in leg chains, and he had never broken his leg chains, sort of peaceably walked about in his enclosure. And right before this tsunami, he snapped his leg chains and ran and somehow broke out of the zoo. And there were other cases documented where, for example, antelope-like animals in a herd running up the mountains, and people were actually saved from the tsunami because they said, oh, I don't know what's going on here, but we're following these animals. So the fascinating thing about the Sumatra tsunami is that though we found over 230,000 human bodies, we found, I've heard this in multiple sources, I don't know if it's 0, but what I have read reported is we found 0 animal carcasses because the animals could feel it and they got out of the way. So we could look to animals for this. So last week I told you I'm not going to tell you about energy because I don't feel like people have a good approximation for energy. But this earthquake that was so large that created this tsunami was the equivalent of, let's see if I can get this right. Sorry, I should have written it down. 45,000 nuclear bombs all going off at the same time at the same place. So it was an enormous release of energy. I know it was 10, 3 times 10 to the 17 joules of energy. So if you do have a feel for energy, it's just a gargantuan amount of energy that came out of the Sumatra fault zone. There's a picture of one of the villages. To me, again, you can't relatively value human life, but the back one, the Sumatra tsunami, these villages were so poor. There was virtually no emergency response. People are walking around barefoot. It was the most well-funded internationally relief effort ever, but it took a while to get to the people. So it was much more prolonged and protracted and heartbreaking than the immediate relief that Japan saw. Here's a picture of the wall of water coming over the seawall, the Japan tsunami, dynamic, awful video. Yeah, you saw the video. This is the biggest earthquake in 1,200 years. It was a magnitude 9.0. I think I talked about it last week briefly. It shortened Earth's day. So the caused Earth to speed up. Granted, it was by about 2 microseconds, but still, we all got our days shortened as a result of this earthquake, and it generated a series of waves that were 33 feet high in a coastal low-lying area. Very, very tough. Another picture, and you saw the video here. What can we do? We talked about this the first day of classes. Monitoring is the best thing to do. You're not going to lower the property damage as a result of monitoring. Here's a picture of the Pacific Warning Center. This is what it looks like pretty much today, a low-tech system. So the monitoring helps us to evacuate people, get them to safety. Another thing that you can do is to implement building restrictions in areas where tsunami can happen. So, for example, this top picture is the 1940 Hilo, Hawaii tsunami, and it just devastated the port region. There were all sorts of buildings there. You see the parking meter that probably takes pennies, if not nickels, all were bent over. The rebuilding efforts involved making that port into a park. So you see this park here. And if a tsunami were to come in here, you're not going to cause millions or billions of dollars of damage anymore. Seawall construction, these can do double duty. So these can mitigate or lessen the damage as a result of a tsunami coming in just as easily as they can mitigate damage from a storm surge in a hurricane, which we'll talk about next week. So, right, they also can possibly mitigate some sea level rise based on climate change. The danger here, right, is that the Japanese people in this region had this over-reliance on the engineered structure, so they were standing on top of the seawall when the tsunami actually overtopped it. Education, excellent. We talked about this the first day of classes. I don't want to be redundant. If you educate people that the bay retreating is the first sign of a tsunami, it's amazing. This stuff doesn't always get passed on anecdotally. And the Lituya Bay tsunami, sorry, I keep mixing these up. The Lisbon 1755 tsunami. Again, if anyone's interested, I have a whole lecture on this. It's fascinating, absolutely fascinating. It's this paradigm shift from the work of an angry, vengeful God to these being natural processes. Amelia, yes. But so when the tsunami was happening, the first thing that happened is the water came out of the bay, the Tagus River going out into Lisbon. And so people were walking on the seafloor. There were actually shipwrecks there. People were finding gold and all sorts of treasures from the shipwrecks. They were having a field day until the wave came in. So educate people. If you feel the land shake, if you see the water retreat, looks like a freaky low tide, get out of there. Evacuate vertically, or if you don't have time to evacuate, if you don't have time to get out of the area, evacuate vertically. Don't go anywhere near rivers. Amelia, you had your hand up. You can just unmute.
Hear me okay? I have some mic issues.
Yes. You have what?
Mic issues usually. I think I get that double speak. The static that you can hear. I don't know how to fix it.
Oh, I can hear you.
Okay, great. We just had some really good comments and questions in the past couple minutes. People were kind of theorizing about low frequency sound in the centers, which I thought was maybe a side topic that might be good to flag.
Say that again.
Talking about low frequency sound sensors and the way that.
Oh yeah, right.
Pick up the tsunami vibrations, etc. I just thought that was good. Actually asked about the benefits of building an inert seawall versus cultivating farms.
I'm so sorry. You're like coming in and out, and I can't hear you. So maybe Amelia, can you write these into the discussion board, and I will answer them right at 7:30. I can't hear what you're saying, and I also am looking at the clock, and I have 3 minutes according to my self-timed situation today to finish these last couple of slides. Not in any way to not answer your question, but we can do it on the discussion board if that's okay. Or at the end of class. Let's see how far we get with the end of class. And low frequency sound, yeah, absolutely. That's a good way to predict or to monitor that a tsunami is coming. So this picture is the Lituya Bay, and it was interesting because I was lecturing about it last spring, and a student came up after and said, oh my gosh, I was just in Lituya Bay and on a cruise with my family. And so this is a picture that she took of Lituya Bay. And what you can see is those majestic mountains. So what happened is there was an earthquake behind the mountains that triggered a landslide that dumped all of this material into this bay. This is a fishing village. So that's a picture of Lituya Bay. So what about you? And by you, I mean we who live in Cambridge, Boston, the whole Atlantic seaboard. Yeah, anywhere from Maine down to Miami. So I'm sure you're all aware that there are the gorgeous, beautiful, amazing Canary Islands, gorgeous place to visit, fabulous. And you can see that there's the blow up of where they are off the coast of Africa. Then you blow it up and you see these 4 Canary Islands. And so what you're looking at here is there's the green arrow, island called La Palma, and the La Palma has 2 volcanoes, Cumbre Vieja and Cumbre Nueva, new and old. And then I'm sure you recognize this word here, right? Caldera. So this was a volcano that was so violent that it went off and collapsed onto itself. So we have a volcanically active island. Now I'm going to turn it sideways so you can see it in profile view. And what you have on the y-axis is the elevation above or below sea level. So there's sea level. So you draw that over. There's where the sea level is, more or less. You have latitude, longitude. So this is the La Palma, Cumbre Nueva, Cumbre Vieja, and then the caldera is here. Any guesses? You can type it in. What this vertical scarp is right here? I'll give you a hint. We talked about them last week. Anyone? Anyone? So this is an earthquake fault zone. So there was a downdropped block. So you have an earthquake fault boundary superimposed on 3 volcanoes. And then maybe you speak Spanish, maybe you don't. To those of you who don't, maybe you can back into what do you think zonas de avalancha means? Landslides, right? So this is a precarious situation. There's a volcanically active fault line landslide situation directly across from us. And what would happen is not just a tsunami, but a mega tsunami. It would wipe out every city on the eastern seaboard and most of Europe. This is a picture of the run-up heights. And you see that the whole eastern seaboard would be demolished, the Caribbean would be demolished, and it would kind of back around to Europe and would destroy a lot of the east coast of South America as well. And it would bounce back and hit Africa. So when would this happen? Well, it's difficult as a geologist to speak in terms of the human time scale. It could happen 10 million years from now. Could happen right now if anyone's not watching TV. Maybe it's going on right now. I'm just kind of joking in the realm of scaring you. In reality, the volcanoes are not active right now, nor is that fault boundary, but there is debris building up that could be a landslide in the future. So that's it for tsunami. So we're going to spend the next half of class on